Well, we're talking about graphs, right? That's what we started talking about last time. Graphs. Graph theory. Just to refresh our memory on the basic terminology, a graph is something which looks like this. This is an example of a graph, right? It has dots connected by lines. That's called a graph. The dots are called, each of these dots, each dot is a vertex, and the lines is an edge. These are the words that we have been discussing. And we also talked about the degree of a vertex. The degree of a vertex is a number. It is the number of edges meeting that vertex. So in this example, if I were to write down the degrees of each of these vertices is the plural, like this one over here, can anybody say what's the degree? Show me the fingers. How many edges are touching this dot here? The fingers say 2, right? I see 2 edges. So the degrees, if I were to write down the degree of each one, that's a 2. Down here, this is a 3 because there's 3 edges here. This one over here, that would be a 4 because I see 4 edges at that vertex. I hope everybody's clear on how I'm getting these numbers. Those are the degrees. And the other ones, they all have degree 1. Those lonely boys have only 1 edge going into them. All right, so those are the degrees. And one last, actually there were 2 more words that we talked about. One was a path. So a path is some sequence of verts connected by edges. And a circuit is a path which starts and ends at the same vertex. And these are all the terms that we talked about. Nothing too fancy about any of this. A circuit is a path starting and ending at the same vertex. So if I had, for example, let's say this graph here, labeled A, B, C, D, then something like A, B, C is a path, which you imagine I start up at A and I go to B and then down to C. So that's a path, A to B to C. But something like DAC is not a path. That's because there is no edge from A to C. So you can go D to A, but you can't go A to C. So that doesn't count as a path. And what would be, can anyone give me an example of a circuit in this graph? A, B, C, yeah, all the way around? Sure. You could do A, B, C, D, A, right? When we write a circuit, we write the same thing at the start and the end. So A, B, C, D, A is a circuit. Great. Sorry, I'm off the heezy. A, B, C, D, A is a circuit, right? You could also say something like A, B, D, A, that's a circuit too. Okay, excellent. These are the basic terminology that we use to discuss graphs. There's one more basic concept, which is a very ordinary concept, but actually it's kind of difficult to write down what the definition is, but I will say what the idea is first. Graphs can be connected or disconnected. These are opposites. Every graph is either connected or disconnected. And what I mean by that is a graph is connected. So Actually, every graph that I've drawn so far has been an example of a connected graph. That right there is connected. What it means to be connected is basically, it's like all in one piece, as opposed to something like this is disconnected because it kind of has two separate chunks to it. This is disconnected. Disconnected. Come on now. Right? On some kind of intuitive level, what it means to be connected is sort of all one piece. And what it means to be disconnected is kind of like more than one piece, right? That's the idea behind connected versus disconnected. But what I said before is, so I hope everybody agrees this is a simple concept. But it is not simple, actually, to write down an actual definition of what this means. So you could say connected means all one piece. But then my question to you would be, what exactly do you mean by piece? And you might answer something like, well, yeah, it's all like one thing, which is all like connected to each other. But then you just use the word connected again, and I'm not sure what, like, you can't use the word connected again to make a definition for the word connected. All one piece, I put that in quotes. That's not a legitimate definition unless you have some kind of way of defining what exactly do you mean by piece. And the word piece has to be defined in some way that doesn't refer to the word connected. All right, this is a little bit complicated, and I thought it might be fun. I don't know how successful this is going to be. I thought it might be fun for us all to take a few moments. I would like you to talk to somebody nearby and see if you can come up with a real way of saying what connected means. You should not be using words like piece or chunk. You definitely should not be using the word connected again to define what connected means. So what I would like is, let's make a real definition of what it means to be connected. Of this word, connected. And this real definition should be using our sort of graph terminology that we've talked about, that I reviewed just a moment ago. Probably not all of those terms, but this is my little hint as far as where to get started. Your definition should use some of those terms, and you should not use words like pieces or chunks or groupings or something like that. You have to make a real definition using our graph theory terms. All right? See what you think. I don't know if you have any ideas, but I would like you to chat with the people nearby, and then I'll give you a few minutes, and then we'll see if we can come up with anything. Everybody understand your job? This is a little abstract. I hope it's not too early in the morning to have some kind of out-of-the-box thinking. It's not horribly out of the box, but you should be using words, like these. I know you can't see them anymore, but path, circuit, degrees, vertex, edge. You don't have to use all of those words. All right, chat with your friends. See what you think. I'm going to walk around and see how you're doing. I would be happy to give some hints. Most of you are starting with That's a good place to start.
I kind of want it to be like no matter where you start, no matter what place you start, you can get to another one. Yeah. Through the edges. Yeah. There you go.
Yeah, I would say. You guys get anywhere? You want a hint? You don't need to. How's it going here? I'm not sure what you mean. Like those two examples that I did, like the first one, you would say they are all attached to form a pattern. Like this one actually just straight up looks bad.
Right.
But that one does go
Oh, yeah.
This is on the right track. You guys getting anywhere? Yeah, what'd you say? Each path is connected to a vertex. I'm not sure. Each path. So we use the word connected, which I don't really like. Each I'm not sure exactly what that means. You should be saying something about paths. This is a good idea. But maybe
Oh, actually.
you got it. Anything you got anything?
Yeah, me too. Yeah, I Oh, I'm
Like, I don't know what you mean by space.
really. I never really care. I don't really care about holidays. Yeah.
A little vague. I would say you should write say something about paths.
bold.
This is my hint. Something about paths. Maybe we can chat about this. I don't know if this is enough time. As I was walking around, I saw some people had some good ideas. Some people had some ideas that I didn't really like. I hope you don't mind, by the way, me saying that I don't like your ideas. This is not a judgment of you personally. I know essentially nothing about you personally. So you very well may be a great person, even if I don't like your definition of connected. Anybody want to offer a suggestion? Yeah, what do you say?
We said a connection in a graph is when all verts are attached to edges, which creates a path or paths.
Okay, I like, so this is, I don't unreservedly like this, but I like a lot of this. Could you say that again? I'm going to try to write down. All.
A connection in a graph is when all verts are attached to edges, which create a path or path.
All verts are attached to edges, which create a path or paths. Is that what you said?
We just did like path with like the parentheses S.
Okay. Paths. Great. So so first of all, this is a hint that I gave to many people. What you eventually say should have something to do with paths. All right? So the fact that you're talking about paths, I like. All verts are attached to edges. See, something that I don't entirely like about this is, for instance, this one right here is disconnected, but I could still say, like, okay, this vertex, it is attached to edges which make a path. And this vertex also is attached to edges which make a path. I think maybe what you mean is somehow like all of the vertices together are on a path or something like that. I'm not sure if that's what you mean. Did anyone have this is on the right track though. Anyone have another suggestion? I know I heard some ideas out there.
Does it make a difference if we say, like, instead of edges, just say all lines?
I would rather say edges. I mean, these little lines, they're called edges, so we might as well say edges. Anyone got another idea? I heard some other notions. Shall I just call on one of the groups that I saw some? How about you guys? Because I liked something that you said. Did you have a final answer that you wrote down?
I had said something like, kind of no matter which vertex you start from, you'll be able to get to any other vertex following the edges.
Yes, this actually is pretty much what I'm going to say as my true definition. She said, no matter which vertex you start from, you can get to any other vertex by following a path. So that is true here. If you say start here and want to go here, you can do that. You can actually get there from here. That is not true here though, because for instance, if you wanted to start here and get over here, you cannot get there from here by a path. This is the idea of connected. So I'm going to write, this is sort of my final answer, which is basically what she said, but I'll write it a little bit differently. I say a graph is connected when I will say any two verts. She's leaving right when we get to the good part. Any two verts can be joined by a path. Right? Given any two vertices, you can always get from one to the other along a path. This is the definition of connected. All right. Another way you can say this, so I heard a slight variation of this as I was walking around. It seemed like some people were saying something like connected means that you can make one single path which actually covers up the entire graph. Some people were saying something like the entire graph is a path or something like that. This is another equivalent way. So that is also correct, although in practice, this right here is easier to use as a definition. So connected when any two vertices can be joined by a path. And I should say the opposite of this would be disconnected. And specifically, what that would mean, Disconnected means the opposite of any two vertices can be joined by a path. The opposite of that would be there are two vertices that cannot be joined by a path. So disconnected means there are some verts which cannot be joined by a path. Right? And the picture of that would be, something like what I said before. Something like this. In this case, for instance, like that guy and that guy, these two have no path between them. And that's how you know this is disconnected. Right? Those two vertices in this graph, there is no path which can lead you from one to the other. And that's why that graph is disconnected. Excellent. Any thoughts about that? The moral of the story here is sometimes even an easy concept, like I would say this is, I hope that everybody agrees with me that this is basically an easy concept, disconnected because these are in two different pieces, right? But even an easy concept sometimes can be very difficult to pin down exactly and say what a clear definition is, all right? And I would like to, so all of this little exercise, which I feel like it went okay. This is actually, I sort of feel badly that I asked you to do all these math chat questions, but we haven't really been doing a lot of them. It's because I haven't really had time to think about them much over the past few weeks. But this is actually sort of in disguise my effort to address this math chat question contributed by one of you. So thank you for this question. Whoever you are, I'm not going to name names. How does math get discovered? I changed one of the words in your question. I hope you don't mind. The original question was, how did math get discovered? I'm going to say, how does math get discovered? New mathematics is being discovered all the time by, mostly by math professors who also do research on the side. And I am such a person, such a man. I do math research of my own. I did some this morning, in fact, in the shower, and then I continued when I got out of the shower. math research still happens. New mathematics is still being discovered. And how exactly does that happen is basically like what you were all just doing. It's usually people working together, starting off by saying, and then you sort of chat with other people who are interested in the same questions, and hopefully if it goes well, you come up with something. But I think actually the process of creating new mathematics is actually kind of similar to what you think doing math is like. It's like sitting around and thinking about stuff and being frustrated a lot of the time because what you're thinking about doesn't make any sense, and eventually figuring it out, hopefully. This is how math gets discovered. And I would say one thing that maybe most people don't appreciate about how math gets discovered is often, so it is just people sitting around thinking about stuff. That usually is how math research goes. I will just say one sort of fun fact. Often the questions and definitions are harder than the answers and proofs. Sometimes the hard part is just figuring out what kind of question you're even asking, or the hard part is just figuring out what you have some idea in your head, but you have to figure out, how do I actually write this idea down in a formal way that really makes sense? And this is a huge obstacle in generating new mathematics. It's not just about answering questions that nobody knows the answer to. It's also about generating questions and generating new ideas which nobody has ever thought of before. This is my opinion about how does math get discovered. This question is an interesting question, but I'm not sure, does anybody have a point of view about this? I assume that none of you have tried to discover new mathematics on your own. Although you could. It just involves sitting around and thinking about stuff. The major obstacle is ordinary people, and even me as a researcher. It's hard for people to come up with questions that nobody already knows the answer to. If I just ask you to give me a math question that you think has never been answered by anyone ever, almost nobody is able to think up such questions to even start answering. But that's the hard part. Any thoughts about that? I recently did a research project with another professor friend of mine. And the project, the first couple weeks, we would meet and talk for an hour or two, just like rambling about nothing, because we had nothing to talk about, or we couldn't figure out what we were trying to even think about. And he asked me once, like, so is this what math research is, just like sitting around and talking about stuff? And the answer is yes. That's how it begins. All right, I hope this was an interesting math chat. Thank you for the question. And what we just did about the definition of connectedness was meant to be a demonstration of how it usually goes. And most of as I was walking around, let's be honest here, most of the little groups didn't come up with something that I actually liked as a definition. But this also is the experience of a true researcher. Like, almost everything you do is wrong. Every so often you do something right. This is true in science also, and in mathematics also. I will spend, if I'm working seriously on a project, I'll spend maybe 2 or 3 hours a day working on it. This is sort of my limit. After that, I can't think straight anymore. But usually a typical 3-hour day, most of that work that I did ends up being bogus. Like the next day I realized I was mostly wrong about everything. But it progresses very slowly. All right, great. It's a little different from being in a math class. In an ordinary class, in a math class, if you're usually wrong, you do terribly in the class. But researchers are usually wrong. It's just you're right every so often. And those are the successes. All right, I think this is enough chat about this. Thank you for the question. How did math get discovered? How does math get discovered? All right, let's talk about something else. So If you look at our big checklist of topics, the first one about graph theory is, it says something like, well, I can see, just basic terminology for graphs. Paths, degrees, connectedness. All right, so we've talked about, these are all simple bits of terminology here. And the questions on those terms will be fairly typically easy. The next section is about, this is sort of a strange name for a section because I didn't know what to call it. Imagine a graph. What I would like to talk about is starting to see where graphs arise in real life. Graphs actually do arise all the time in the real world as sort of mathematical things that you can think about mathematically. Not really so common as numbers. I mean, numbers really arise all the time in the real world. And when people do math in their real life, they're usually talking about numbers. But actually, graphs arise often in the real world. For example, here is a simple sort of real life type scenario. This is not a true story, but this could happen in the real life. Let's consider a graph where each vertex is one of my kids, and their ages are 3, 7, 12, 12, 18, and 19. This is not a true story. I have 2 kids. And 2 is plenty for me. All right, let's say each vertex is one of my kids, and these are their ages. And let's say each kid is friends with any others whose ages are within 5. All right? So like the 19-year-old is not really friends with the 3-year-old naturally, but the 19-year-old is friends with the 18-year-old, and so on. All right? This is meant to be a vaguely realistic situation. Can you express this whole scenario using a graph? And by looking at the graph, can you decide anything or say anything about this scenario in real life? So each vertex is one of my kids. So I'm going to, there are 6 of them, right, with those ages. So I'm going to draw a graph, which, I mean, I don't know where the edges are going to go, but I'll just start with 6 vertices, right? And they have those ages. Maybe I'll just write those ages next to them. I have the 3, the 7, a 12, another 12, a 18, and a 19. These are not the degrees of these vertices. These are just labeling them according to their ages. And then each kid is friends with any others whose ages are within 5. So I'm going to use edges to represent the friendships. Ages represent the friends. So the 3-year-old, edges represent the friends. Where should the edges from the 3 go? According to the scenario that I described, who is the 3-year-old friends with? Somebody can shout it out. The 7-year-old, yeah. Any others whose ages are within 5. So the 7 is within 5 of 3, but nobody else. So the 3 has an edge going to the 7. That's their only friend, because everyone else is way too old. What about the 7? Okay, well, the 7 is friends with the 3. We already said that. But also with the 12s, right? Because 7 and 12, I said within 5. I mean 5 or less. So the 7 is friends with the 12s, both of them, here and here, right? How about the 12s? Well, the 12s are friends with the 7. Are the 12s friends with the 18? I say no, because the difference there is 6 years. The 18 and the 19 are friends with one another, but not with any of the others. All right? So it's like so. And I should say the 12s are friends with one another, right? I think that's what the graph looks like. The edges represent the friendses. All right? Now, does this graph tell us anything about this whole scenario? I would say I mean, this is not all that insightful, but I would say, looking at the graph, the fact that it's disconnected, I can tell that these 6 people, when they're sort of hanging out, I expect the 18 and the 19 to be doing their thing, and then all of these other ones to be doing their thing, right? They should naturally, this group naturally will separate into 2 separate kind of clusters of people when they are hanging out doing what friends do, all right? And I would also say the 3-year-old here will feel sort of like an outsider in this group, right? Because the 3 is only friends with the 7 but not with the 12s, but they're all still going to be hanging out together, all right? So you can deduce sort of social relationships based on viewing this thing as a graph, right? The whole idea is, can I represent this structure as a graph and then say things about the scenario based on the structure of the graph? That's what this kind of imagine a graph sort of thing is all about. All right, I got some more examples like this. So a typical homework problem about this would be, you know, maybe I would describe this scenario. I would ask you to draw the graph and then say something about what you notice about this graph. In this example, I noticed that it's disconnected, and what that means in terms of the real life situation is, you know, basically these people will not hang out with these people. Something like that. All right, let's try another example. This one is actually impossible to draw because it's too big, but we can still think about it. So let's imagine a graph where I have to tell you what are the vertices and what are the edges. So each vertex is a Hollywood actor. So this graph has many, many vertices. Like every actor you've ever heard of is a vertex in my graph. And each edge, so I'll say there is an edge between 2 actors if they appear in a movie together. All right. So this is a very big graph because it has like thousands of vertices. Every actor is a vertex. So this is a very big graph, and it has many edges in it. Every time 2 actors work together in a movie, that makes an edge between them. All right. So for example, now you can't draw this, so this graph is too big to draw. But you could draw a little piece of it. So a piece maybe looks like something like, how about, here is a vertex representing Chris Evans, Captain America, right? True specimen of a real man, am I right? Chris Evans here has been in several movies, so there are like many edges coming out of here, right? Because he's been in a lot of different movies. Maybe one of those movies, he appeared, more than one in fact. Let's say here's another one, Scarlett Johansson, remember her? I think that's how you spell it. So Chris Evans has an edge to Scarlett Johansson because they were in all those Marvel movies together, all right? And then she has also many edges going to other actors that she has appeared in. How about, here's another one. I'll put Adam Driver, that guy. He was in a movie with Scarlett Johansson, the one where they're like yelling at each other in a room. There was a meme about it. I didn't see this movie, but they were yelling at each other in a movie together. And Adam Driver was also in a bunch of other movies. But to my knowledge, Chris Evans and Adam Driver were not in a movie together, so there's no edge right here. I don't actually know if that's true, but no edge here. Maybe I'll put a sort of dotted line. No edge there, because those 2 guys have not been in a movie together. I'm not sure if that's really true, but this is what I am trying to imagine. All right? The true graph is way too big to draw the picture of the whole thing, but this is basically what it looks like. All right. Can we try to answer some questions then about this graph? So some basic questions. I would ask, here's a question. What does the degree of a vertex represent in this graph? Can anybody say in words, like in terms of the thing that the graph is meant to represent? What does the degree mean? The degree, remember, means the number of edges that meet one of these vertices. Any thoughts? Yeah?
Is it the number of times one actor has been in a movie with another?
Yes, she says the number of times some actor has been in a movie with some other actor. That's true. So if I said, like, for instance, if I told you the degree of Chris Evans is 59, that means Chris Evans has been in movies with 59 other people. Actually, the true number would be far greater than that because every movie he's in with like hundreds of other people. But anyway, that's what the degree represents. So the degree of some vertex, I'll just say like X, is the number of other actors that X has appeared with. Right? You may have been tempted to say it's another number of movies they've been in, but that's not the case. In this, the way this graph goes, the edges represent these two people have been in a movie together, but it's not exactly the same as how many movies these people have been in, right? Great, that's what the degree of a vertex represents. Here's another question I could ask. How about who has higher degree? Tom Hanks or Tom Green? Anybody know who Tom Green is? He was like a very briefly popular actor in the 90s. He was sort of a weirdo, kind of nerdy guy who was briefly married to Drew Barrymore. He was like everywhere for a year or two, and then everybody promptly forgot about him. Anyway, what do you think? Who has a higher degree in the graph? Tom Hanks or Tom Green? The answer is Tom Hanks, right? Tom Green was in a few movies with some other people, but Tom Hanks has been in far many more movies, and therefore he has appeared with many other actors. So the answer is Tom Hanks. So Hanks, because he has been in more movies with more actors, all right? Great. These are the types of questions that I would ask you to think about when you are, I would describe a graph to you and then ask you basic questions like this. And sometimes the answer might be, I don't know. Like in this case, I could ask, is this graph connected? The answer to that question, I think, is I'm not sure if it's easy to say if this graph is actually connected or not. Because probably, like most actors that you've ever heard of, would be part of this group. Like if you think of any actor you've ever heard of, they probably can be, for instance, connected to Chris Evans by a path of movies they've been in. Chris Evans has been in a movie with this guy, and that was in a movie with this guy, and so on until can you actually get to every other actor like that? I'm not convinced that it is connected. So this, I would say, probably mostly connected, but I'm not actually sure if it really is. All right, I got another example. I got tons here. How about, I'm trying to give sort of a bunch of different variety of examples here. How about another one? Each vertex is let's say a normal full-time student at our dear university, Fairfield University. Let's say they're not studying abroad, just like a normal student who is here living their best life. All right, and two verts have an edge if those students have a class together this semester. All right. So in this graph is also too big to draw a picture of because it has, many thousands of vertices, because every student at the university is a vertex. And it has many edges also, because every student, like you, each of you is a vertex in this graph, and you would be connected by an edge to all of the other students who have a class together with you. So in particular, you'd be connected by an edge to everyone else here with us right now, plus all the other people in all of your other classes, all right? Two vertices have an edge if those students have a class together this semester. I could ask something about what's the degree. How about, rather than the, what is your degree in the graph? You as a student are part of this graph. What is your degree in this graph? I'm not sure it's possible to know like just off the top of your head, but is it, I would say, maybe a little multiple choice. Is it something like about, maybe 3, or is it about 20, or about like 80? Anyone have a thought here? Your degree in this graph. You have to try to imagine in your mind what this graph looks like and what determines. Degree, of course, is how many edges coming out of you. Any thoughts? Nobody wants to say anything. Yeah. 3. I disagree. This is also a difficult thing about doing math research, is most of the ideas are bad, and I have to say to my dear friends, that was a bad idea. It's a painful thing. 3, remember, 2 vertices have an edge if those students have a class together. So when I ask you, what's the degree, is how many edges are there connected to you? That's the same as asking, how many other people are there that are in a class with you this semester? I think the answer is not 3. Do you have a modification? Different idea?
80?
Yeah, I think 80 is more like it, right? There's about 20 other people in this class, but you're in other classes other than this class, right? The degree in this case will represent all the number of all the people in all of your other classes, and including this class also, all right? Which is probably something like 80, maybe even more than that. I don't know what kind of classes you're in. It's something like this one here. This would be the number of all students in all my classes, right? This is bigger than, I don't know what it is exactly, but it's certainly bigger than 3 or 20, all right? This would be the number of all the students in all of your classes. All right, how about, okay, so every vertex in this graph actually has many, many edges coming out of it, right? To the tune of 80, even more than that, what I just drew. How about, is it connected? What do you think? Is this graph connected? This is, if you were looking at the graph, you would answer this question by just seeing if the graph is all like in one piece or if it has separate pieces. That's a little hard for me to visualize. I think it's actually a little easier to think in terms of the real definition of connected means you can get from one vertex to another one by following edges, all right? By following a path. So when I'm asking this question, it's really the same as asking, like, if you just take 2 random students at the university, is it always possible to say, maybe they are not in the same class together, but like this guy is in a class with this guy, who's in a class with this guy, who's in a class with this guy, and eventually get to the other student. Do you think that's possible? I would say probably this is possible. To take any 2 students, They are probably not in the same class together, but it is probably possible to make a path from the one student to the other along individual people who are in same classes together. So I would say, I don't know this for a fact, but I would say probably. And what that means is that given, I'll say, i.e., given two students, they probably can be connected by a path of students, studs, in the same classes. This guy's in the same class as this one, and this one's in the same class as this one, et cetera, et cetera. You can probably make it from any one student to any one other student. All right? I don't know if that's precisely true, but probably it is, I would say. All right? What if, how does any of this change? What if we also include abroad students? I think something about this what I just said is different. If we also include students who are abroad, any thoughts about that? We have only a couple minutes. I think something about this graph changes significantly. What do you say? Yeah?
The graph's gonna be bigger, there's gonna be more connections, probably.
It will be bigger, yes, I agree. The graph will be bigger because there will be more students. What about the connections? I mean, those, let's say I took the people who are here right now, but then I, just for fun, let's also throw in the people who are studying abroad in the UK, right? Are they gonna just join in with the rest of the graph? Or like, what is that actually gonna look like when you add those into the picture? Yeah?
It'll be less connected, because there's a class connectivity without the student.
Yeah, right. I think when you include the abroad students, those new ones will be disconnected from the ones who are here. Because none of those people are in any classes with any of the people who are here, right? Because they're too far away. I think this is true. So if we include abroad students, then basically what happens is then it becomes disconnected. You end up with, say, a bunch of things over here, which are, you know, sort of at home on, you know, here, and then you also have a bunch of people who are abroad over here, and they might be in classes, the abroad people might be in classes with each other, and the people here might be in classes with each other, but there's never going to be somebody who's abroad now who's in the same class as someone who is here now. And so now the graph becomes disconnected. There can be edges over here, and there can be edges over here, but there is no edge going across to sort of bridge the gap. All right? All right, I think that'll do for today. We'll do a couple more of these next time, and you'll have some on the homework too. Let me know if you want to talk about the homework which is due tonight. I think I already have some folks who are going to chat in my office right now. You are free to join in if you're interested.